Okay, I paused it for I paused the recording for a moment to look some stuff up. It looks like my math capabilities are a little bit below what what would be needed to solve this differential equation, but I did find that this is a single order ordinary differential equation. It's linear. So if you put it in this form right here, I just rearrange the equation to make this form, then you can solve the differential equation, and I'll show you what those rules are. But the math gets very intensive. So if you can get the equation in this form right here where you have the derivative first, let's see if I can do this right. So you have the derivative first, and then you have a function of time. I is a function of time, so this should be I of t right here. And then you have I'm sorry, 10 is your function, and then you have your variable you solve for. Y here is I here. It is equal to some other function of time. The only thing that needs to happen to this is we'd have to get this derivative by itself, so divide everything by L, and that's what you would have there. So that would be in the correct form to solve the first order differential equation. So if you can get that far, if you can get it to that, then here's how you solve it. Just a second, let me find it again. Here's the solution right here. This y of t is equal to all this, everything in our equation you can see, and then solve it with this method. But if you do that, you're going to be taking the integral. See this mu of t right here? You're going to be taking the integral of a cosine function. I'm sorry, that's the integral of 10 right there. But then you're going to take all this. That'll be easy. That'll be just a constant. But then you're going to take the integral of a cosine inside of here times whatever you find from here, and then you're going to have a constant for your initial conditions, and then you're going to divide the whole thing by this again. So that gets very intensive with differential equations. If you've been studying up on the math anyways, you might be able to easily solve that, but it's been a few years for me. But I'll show you the way I would do it, because my method is a lot easier, and that is with Laplace transform. And I know you said it's been quite a bit of time with you doing this, but I want to show you how quick and easy it really is. So basically what the Laplace transform does is it allows you to take a function of time and transform it into a function in the frequency domain, and then you can solve the equation using algebra instead of differential equations, and then you can take the inverse transform back to the time domain. So basically it's a way to solve the equations quicker without having to solve differential equations or know all these rules right here that I was just showing you. So the way we do that is we just have a simple table right here. Well, I wouldn't say simple, but the method is simple. And we can see on the left, on both of these sides, that's our function in time, and on the right, that's our function in the frequency domain. So, going back to this, we have a cosine function right here. So I just look on the table. I can see that we have a simple cosine function right here. So if we want to transform this into the frequency domain, it's s over s squared plus a squared. So I'm going to transform all this, and I'm going to say, also the 20 is a constant, so that comes out, and it's s over s squared plus a squared, where a is our 120 pi. And then if you take the Laplace transform of a derivative, let's find that on this table here. So that'll be s times our function in the frequency domain, which the capital I means we're in the frequency domain, lowercase I means we're in the time domain. Our function in the frequency domain minus our function in the time domain at time 0, which is actually the value right before we close the switch. So we should say time 0 minus. So we could take all of this, solve for I of s, which will basically just be a algebraic equation, and then we can take the inverse transform, and then we'll have I of t. The only part we don't have right now is we don't know what I of 0 was, so right before we flip the switch. So right before we flip the switch, actually that's incorrect. We do know I of 0. We solved that in A right here. Because before we flip the switch, we're assuming this switch was open for a very long time. We had current running through this loop as we did last time, and it kept on going and everything was charged up. And we solved for this I1 right here. That's the same thing as our I of 0. So let's see if we can go back to that. Okay, I'm going to find our current here. There it is right there. 7.53 angle negative 87.6 milliamps. 7.53. So, write a note here before. So we had 7.53. That was the angle. So I'm going to put this in the time domain. Cosine of 120 pi t angle, I believe it was negative 87.6, negative 87.6. That doesn't look very good. And that was our function of time before. So we can say I of 0 minus is equal to 7.53 7.53 cosine. Now we're going to plug in 0 for t. So 0 times 120 pi is 0. So it'll just be 87.6 degrees in milliamps. So let's get our calculator going. Okay, we're in degrees, so we want to take 87.6 negative, take the cosine of that. Let's see, make sure that makes sense. Yep, it should be very small. Multiply that times 7.53 times 10 to the negative third. And we get 3.15 times 10 to the negative fourth. We could also call that 315 times 10 to the negative 6. So that would be microamps. So that's this value right here. So I'm going to erase that and insert it there. Okay, so let's see. We were transforming this derivative, so we had s times the function in the frequency domain minus the function in the time domain at time 0. So that's 315 times 10 to the negative 6. So minus, going to pull our constant 10 out here. And then if you take the transform of the function, you basically just get the function again, but in the frequency domain. So this is going to be capital I of s equals 0. Okay, so let me clear some space here. So I know this looks pretty time consuming, what I've been doing so far, but keep in mind, solving the differential equation is going to be time consuming also, and you're still going to have that initial value that we just solved for, even if you solve it with the differential equations, because that's going to be your constant of integration. That's going to come into the calculation. So no matter what, you're going to have to do what we just did right there. So now our goal here is to solve the algebra for I and then take the inverse transform. So let's go ahead and do that. Let's see, I'm going to make everything opposite here. Okay, so we have I of s, which for simplicity I'm going to leave the of s out. So we have I times L s, that's those two, so So we know we got rid of that guy. Plus 10i, or plus 10. I'm just doing algebra right now. Equals 20 s over s squared plus 120 pi squared minus 315. Actually, I made that a plus. This is a minus. That'll become a plus on the other side. Times 10 to the man. Negative 6 L. Okay. So then what we want to do is we want to divide the whole side by LS plus 10 on both sides. And then we will take the inverse transform and we'll find, after we divide by this portion right here, we'll have I by itself. We take the inverse transform of both sides of the equation, we'll get I as a function of time. So that will be our first part. After that, what else do we have next here? Oh yeah, we want to solve the other form of the equation. So I'm going to leave that to you at that point because I don't want to waste your time doing a bunch of algebra. But basically, if you Google Laplace transform table like I did, and this comes up on images, so Google images, and then that's it right there. So what you're going to get is you're going to get an equation, I equals a bunch of stuff added together and divided, right? So if I was to pretend like this right side over here was all I ended up with, you could recognize that you would see an s over s squared plus something, and you would look at this table and say, okay, well, where do I see s over s squared plus something? And that's the cosine. So you know you'd have a cosine with an a inside of there based on whatever your constant is down here. And so forth. If you end up with another common one to end up with would be 1 over s minus a or 1 over s plus a, and then you know you'd have an exponential in your time domain. So that's that part. So our other form of the equation, remember we wanted to use superposition to pretend like this source doesn't exist. So I'll redraw the circuit one more time. We have an R and an L, an R and C. So we have an R, we have an L, we have an R, we have a C. Remember, we had that other source over here on the left. We're shorting that out, pretending like it doesn't exist. So, since we're running out of time, I'm just going to do this in generic terms here. And let you do the actual math. Okay, so for this, since we have a DC source, this is DC. We can use some tricks to where we don't have to use differential equations or Laplace transforms. Instead, we can use these rules right here. So here's a capacitor with a DC source, as you can see on the left here. You have an RC circuit. Well, if you know you have a voltage source and an R and a C and a switch in there, and you're closing that switch at time equals 0, you know your current is right here, I. So here's what I'm trying to show you. I'm going to draw two currents here. And that would be I1 and I2. I1, I2. So essentially, that's exactly what we have, just like they were showing. So we know that the current I2 is equal to VB, or V of the battery in this example over here. So I'm going to call this, V. It's going to equal V over R, so R2 in this case, times e to the negative t over R times C. There's I2. I1 will be, let's find where I had the other one. Let's see, it looks like I accidentally lost it, so capacitor, so we're looking for inductor transient. By the way, most of this information I get is from hyperphysics, so if you just Google something, they have some very good stuff for you. So the current in the inductor will be VB, so V over R1 times 1 minus e to the negative t R over L. So that's what we call the time constant tau for a capacitor is RC, and the time constant tau for an inductor is RL. So this is basically saying the amount of time that it takes it to decay enough for it to not matter. So think of it this way. For a capacitor, if you have trouble remembering the way these equations are, One of them is 1 minus, the other's not. For a capacitor, if we have a voltage supply on it, it's going to start charging up and developing a voltage because you can't change the voltage instantaneously, but eventually you'll get zero current through that capacitor, because eventually once it's charged up, a capacitor in a DC circuit, remember DC only, capacitor acts like an open circuit. So you know I2 should eventually become zero. So that makes sense, because think about if you put a negative infinity for t here on I2, the limit as t approaches infinity will be 0. Inductor's opposite. After it charges up, it acts like a short circuit, so just a wire. So your current, after a long period of time, after your inductor charges up, basically all your circuit sees over here is your resistor. So your current will be your voltage divided by your resistance. So look at this equation down here, it makes sense. Because as t approaches infinity here, you're going to have 1 minus 0, so you'll have 1 here. This whole exponential will mean nothing, and your current is just your voltage divided by your resistance, because your inductor doesn't matter anymore. So that's how you solve for I1 and I2. We did the same thing in the other part of the superposition. So keep in mind that your I2 or your I1 will be the I1 that you find here from this, whether you decide to use differential equations or Laplace transforms. It'll be that I1 plus the new I1, which is this. Your I2 in the other circuit was 0, so 0 plus this I2, this will be your final answer right here for your I2. Okay, so let's go back here and look at what else we need. We need I1, I2, and V1. So if we need V1, we will need to use a different form. Remember, we used a loop equation to solve for voltage in order to find the current. So I know it sounds kind of backwards, but remember, we did a loop equation the first time around the whole loop. And that's because we knew that the voltages were all dependent on the currents here. So the next thing we'll need to do is we need to find the voltages. Well, if we know the currents, because we're about to solve for them, we can find the voltages by these equations right here. So we're going to know this current. This current right here is I1. That's I1 right there. So V1 will be, I'll just write this out, V1 will be I1 times R1 plus the voltage over that inductor, which is L d I1, because DL is, or IL is I1 here, dt. So you're going to find your current as a function of time. You just take the integral of that and multiply it times your inductance. Now you have your V1. So that's how you're going to solve for V1. If S is closed at time equals 0, power dissipated in resistor RL. So this, I believe, will also be a function of time. because your voltage is going to change over your resistor over time, because your voltage over your capacitor is going to change over time. So remember, we use superposition superposition, this is being slow, so I'm just going to verbalize it. Using superposition over here, we decided to solve for I1 and I2. Just add another one to that, your power over RL. So remember, in this first circuit, RL is shorted out, because remember this wire over here, it made everything on the right side of the circuit not matter. So actually you won't have to use superposition, because you're using superposition, but you won't have to sum anything, because the only place where RL comes into the circuit, this is where I have labeled R2, which is actually RL, is in this portion of our superposition. So you solve for your I2 right here. There's your I2. Multiply it by your resistance, R2, and you have your, that would be for your voltage. You can square this and multiply it times your resistance for your power. I squared times R is power. So that's that. It will be a time-dependent function, because at first there will be a lot of power dissipated in this resistor, but at the end of the function there will be no power dissipated in this resistor, because your current going through it will be 0, because this capacitor will act like an open circuit eventually. So that's that. I know I rushed through a lot of this, and I didn't explain everything, and I didn't finish the problem for you, but you know, we didn't have much time, and as you can see, this is a very complicated and tricky problem. It's basically a very advanced electrical engineering problem that I would expect to see in a junior or senior level electrical engineering class. So I left you with enough, hopefully, to finish it on your own. If you want to have another session, I'd be more than happy to. Most of what's left is just math anyways, but I think what you probably wanted the most help on is theory and not math. So I hope this is what you're looking for, and like I said, feel free to let me know if you'd like to have another session. I'd be more than happy to.